Acha. So basically, what is an object and an image? Object and image. Object is the point of intersection. We are talking about point object only. So many point objects will make a body like that, an extended object. So an object or a point object is point of intersection of incident light rays. An image is the point of intersection of reflected or refracted light rays. Depends. Depends. Say for the image formed by a mirror, then we talk about reflected light rays that will form an image. I mean, the point where the reflected light rays meet, that is the image, and the point where the incident light rays meet is object. For the lens, refracted light ray, the point of intersection of the refracted light rays is the image for the lens. Now we are talking about say mirror. Okay. Now you know what is there can be object uh, and image may be real or virtual. Now when it is real when and virtual when. Real when actually, yes, 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 exactly. So real when the light rays actually meet or really meet or actually intersect, and virtual when the light rays appear to intersect. Uh, Rather, I can say light rays do not intersect really, do not actually intersect. I mean, if you extend the light rays, that will intersect. Is virtual. So, uh, for example, say we show the plane mirror. So this is the plane mirror. Okay, plane mirror. Now, simple. I'll talk about point object first. Say this is an object, a point. Now, you know the laws of reflection of light. So I don't have to discuss it now. No? Laws of reflection of light. Yes, that that was discussed before. Uh, Two laws, na? Incident ray, and this is reflected ray, and this is normal. There are two laws actually. First law says the incident ray, reflected ray, and the normal are coplanar. This incident ray, the incident light ray, the reflected light ray, and the normal at the point of incidence. they are coplanar, and second point was that the angle of incidence is equal to angle of reflection. So angle of incidence is the angle between the incident ray and the normal, and angle of reflection is angle between the reflected ray and the normal. So it's okay, almost done. And say there is a case known as normal incidence also, where uh, both theta is 0. By the way, so from this object, say we can draw light ray here, another light ray, say here, incident light rays. So how they are reflected? Like this, and this was like this. Now, if you produce the reflected light rays, then where will they meet? If you produce this by a dotted line, because it doesn't exist really, then the light rays will meet at the point. So this is I for image, because see, as per definition we know the image is the point of intersection of reflected light rays. Formula refracted, that will later during that lens. So this is normal, again the normal. So this angle is theta 1, this angle is theta 1, this angle is theta 2, this angle is also theta 2. Okay, so this is what type of object, real or virtual? This object, so the object, see, object is real, exactly, object is real, and the image is virtual, because see the reflected light rays, these are the reflected light rays, they do not actually meet at the point, right? If we extend it, so the image or the intersection point here, the image does not actually exist. If it exists, you can cast it on a screen, but that you cannot do. So that is why it is a virtual image. So real object, virtual image. And from similar triangles, you can prove that these objects, so that these distances are same. মানে, if this distance is x, this distance is also equal to x. Okay. Now, next page. Now, a slightly different incident light rays. But this is also incident light rays. And they, I mean, obeying the laws of reflection, you get reflected and meet at this point. So these are the reflected rays. The upper one also reflected. Okay. So here, which is the object and which is the image? Can you say? The point where the incident light rays meet is the object. So this is the object. O for object, and point where the reflected light rays meet, that is the image. I for image. Object is virtual, and so this is virtual object, and this is real image. Exactly. object is virtual and the image is real, and rest all same that these distances, if you calculate from similar triangle, if this distance is x, this distance is x, this distance is also x, no problem. So the same thing holds for an say an extended object also. If this is an extended object, then how will be its image? This is the extended object, this is the image. On a point to point, say for point A the image is A dash, for point B the image is B dash, all following the same laws, right? The distance of the object from the mirror is distance of the image from the mirror. Holds for all points. Similarly, a points C correspondingly C dash. So this one to one you get uh, the image for the extended object. Okay. Now, for point A, if the distance is x1, say xa, then the image of A, which is A dash, it is having the same distance xa, and for B, distance is xb, and B dash same as xb. So this point to point, xc is also xc. So for every point uh, in the extended object, you get an image. So for the whole extended object, you get an image. Now, say this is a mirror. Now, objects, if object, mirror, or both are in motion, then how the image moves? How does the image move? So let's take case by case. Case one. Case one. Say mirror fixed. M. Say a short form. M for mirror. O for object. And I for image. So here M fixed and O moves towards M at speed v. So M fixed and O moves towards M at speed v. And how does I move? I means image. What is the velocity of the image then? If the object moves with a velocity v towards the left, the image moves with a velocity v minus your v towards the right. Simple. Because you can equate the distances. Right? So now the distance is say this is x1, distance is x1. After a certain point, object moves here. Say O, say that is say O1. Now here the image moves to this I1. So now if this distance is x2, this distance is also x2. So these two have same displacement, but opposite direction. Magnitude of displacement is Now case 2. Case 2 here, object is fixed. M moves towards the object at speed v. Then what happens? Object O is fixed. M, the mirror, moves towards the object at speed. How does the image move then? How does it affect image motion? Hmm? মানে you can do like this, x, then correspondingly this is the image I, which is also at same distance x. Now move the mirror by a distance, say d, then you can locate the image. So that is case 1, case 2. Just one more diagram, mirror, and make the object fixed. This is the object and this is the image. So distance is x. So at start distance is x and the mirror moves with velocity v. So this is vt, right? Vt. So now the image has moved to here, say I dash or I1 rather. I1. What is I1? The new position of the image. Okay. Now the distance. So this distance is x minus vt now. This is x minus vt. Now the distance from the new image to the new position of the mirror is also x minus vt. Now you have to find this distance. What is this distance? That's easy actually. From this diagram, you know this correspondingly this distance. Suppose it is d. You have to find d. So d is equal to 2x minus 2 times x minus vt, right? So it is 2vt. T is 2v into t. That means the image moves with how much velocity? Implies velocity of the image equal to 2v to the right. Obviously it is 2v because in time t the image moves the distance 2vt. D has come out to be 2v. Simple. This comes out to be 2v multiplied by t. So the image has a velocity of 2v. So if the mirror moves with v, the image moves with velocity 2v. In the same direction, image has velocity v. Mirror has velocity v. The image will have have twice the velocity in the same direction. This same problem you could have solved it from a different way, in a different way rather. That's see, always you can go to the mirror frame. That is the most useful method. Always. So this is the object, and so you have to find out the velocity of the image. So this uh, velocity of the mirror is v. Now, uh, say let the mirror be the frame. Mirror. Same problem. Same problem. Mirror frame most useful because what happens from the frame of the mirror, from the frame of mirror, the image, so object and the image have same velocities, have velocities of equal magnitude, but in opposite direction. Opposite direction. I mean, if the velocities are perpendicular to mirror surface, then only now. If they are parallel to mirror surface, then not. If you jump up, your image will not jump down. Then it will not be inverted. But if you go towards the mirror, your image will also come towards it, or they are in opposite direction. So let's go to the mirror frame. This is the mirror frame. From the mirror frame, what is the velocity of the object? V. So the velocity of the image will be v here, right? So if you write it vectorially, this vector is velocity of the object with respect to mirror, and this is velocity of the image with respect to the mirror. Okay. Now this is the vector, this upper one here. Okay. Here this vector is what? Velocity of the mirror itself, Vm. Now we have to calculate velocity of the image from ground frame. Velocity of image. If nothing is mentioned, that means it's calculated from ground frame. So Vi is equal to by the relative motion concept, Vi with respect to m plus Vm. So Vi with respect to m, and about Vm. Vm. Vm is also this way, and that's V. That implies if you add these two vectors, implies Vi. Vi is sum of two vectors, 2V. Simple vector sum. Okay. So how many cases we have done? Let's do case 3. Case 3 here. Say if object, see M fixed, object will return as O, and O moves parallel to mirror surface. Then what happens with velocity? Mirror fixed, mirror fixed, and O moves parallel to mirror surface with velocity v. Then what does the image do then? Same thing now. You jump up in front of the mirror. The image in your face will jump down or up? Up now. Same speed, same velocity. So here image has same velocity as that of the object. Okay. Image has same velocity as that of the object. Case 3 clear. एकदम. Case 4 is extremely simple. That here O fixed M moves parallel to its own surface. Then what happens? This is M, the mirror. The mirror moves with the velocity like this V, and this is the object. What will happen to the image? What will happen to the image? Say you have a mirror in front of your face. Move the mirror up. Does your face move up? No. So answer is nothing. Nothing happens. Yes. Nothing happens. That means image is at rest. I at rest. Or fixed. I is also fixed. Okay. So case 1, 2, 3, 4. Now we can combine all the cases. Now we can combine all the cases. Next case, uh, case 4, right? That is what. This is a mirror. First, let me give a simple one. X and y axis are given. X and y axis as shown in figure. This is M mirror. This is object. Here, object has velocity minus 3 I cap plus 4 j cap, say meter per second, and mirror M has velocity, say 2 I cap plus 6 j cap meter per second. Find velocity of the image. So how do you do this? How do you attempt this? How to find velocity of the image? Object has velocity minus 3 I cap plus 4 j cap. That means here in the diagram, see, y axis is along the surface of the mirror. I should have mentioned that. Or mirror surface is the yz plane. Right? Mirror surface is the YZ plane. So this object has velocity. This velocity is uh, 3 3 towards the mirror, right? 3 meter per second, and what else? 4 meter per second upwards. Okay, that is for the object. Now for the image, what about the mirror? Sorry, what about the mirror? Mirror has velocity how much? 2 I cap plus 6 j cap. So this is in this direction. Velocity is how much? 2 meter per second, and one more velocity upwards. It is 6 meter per second. Now looks like really relative velocity, so many things. Yeah. Actually, can you say you can just negate one velocity out of all this? So actually, when you split it into components, there are four velocities, right? 3, 4, 2, and 6. Out of these four, one component you can completely ignore. Yes, the 6j, that 6, that velocity of the mirror is actually not needed. So you don't need it, right? 6j. So we can erase that. So this 6j is absolutely not needed. Convinced now? Why it is not needed? That's what in case we are done in case 4. So this velocity is absolutely not needed. So I'll just erase 7 I cap plus 4. And what we'll do here is, so again you can move to the frame of the mirror. Move to the frame of the mirror. Solve from mirror frame. That is a good habit actually. Mirror frame. When we deal with concave lens, lens, concave mirror, convex mirror, then always you have to solve from frame of the lens of the mirror and then convert it to ground frame. So from the frame of the mirror, velocity of the object. So we are drawing a relative velocity. Obviously this way it is 5, and this upward view, so you can see 4 meter per second. Now object, now this is same for the image, only this component is reversed, 5 meter per second, and this remains same as 4 meter per second. So this whole vector is velocity of object with respect to mirror. I mean combination of these two vectors, and this is velocity of image with respect to mirror. I mean this, and so we can write velocity of image with respect to mirror as, velocity of image with respect to mirror is, as you see, 5 I cap plus 4 j cap. Now velocity of the mirror is how much? 2 I cap. Now I have not added that 6 j cap. Obviously that doesn't contribute. This component won't contribute. So velocity of the image is equal to velocity of the image with respect to mirror plus velocity of the mirror. So that is 7 I cap plus 4 j cap. So the image moves with a velocity how much? 7 meter per second towards x axis and 4 meter per second towards y axis. This is the velocity of the image from ground floor. So prove that keeping the incident ray fixed, if the mirror rotates by theta, then the reflected ray rotates by 2 theta. So initial position of mirror, say it's this initial position of mirror m. Now this is the say initial normal n. Only the incident ray is fixed. Say this is the incident light ray. Now suppose this angle is alpha. So what is the reflected ray? Where reflected ray also have a same angle alpha. So this is the same angle alpha. This is the incident ray, reflected ray. So M for mirror initial position, and N for normal initial, R for reflected ray. So initial reflected ray, later on it will change. Now final, so M dash, N dash, R dash, this will be all this corresponding final, right? Mirror, normal and reflected. Okay. Now mirror rotates by angle theta. So let us make theta. Mirror here rotates by an angle theta. Final position of the mirror, this is denoted by m dash or m prime. So that is angle theta. So when the mirror rotates by theta, the normal will also rotate by theta. This is the new normal, right? New normal. Now we will draw the reflected ray now. Now the new reflected ray. New reflected ray, this one. This is R dash. R dash. So the normal, see, when the mirror rotates by theta, if mirror rotates by theta, then normal also rotates by theta, right? Also rotates by theta. So now let's draw the normal. This is normal. This angle is theta. Initial normal and the final normal. This angle is theta. And so the incident ray and n dash, what is the angle? Alpha plus theta. So this angle of incidence, angle of reflection. So this angle is alpha plus theta. So you have to find the angle between R this way. You have to find this angle. R R dash. This angle phi. Phi. From the incident ray, we can calculate the angles and subtract. So alpha plus theta. So we can write phi is equal to here alpha. This angle alpha plus theta plus alpha plus theta. Right. 80. Total angle. How much is this total angle? Total angle from I to R dash. You can write. Say this point is P point where the light ray strikes the mirror is P. So it is angle I P R dash minus angle I P R, that is phi. So I P R dash is how much? Alpha plus theta plus alpha plus theta. On this one, alpha plus theta plus alpha plus theta minus IPR. IPR is how much angle? See, IPR is actually 2 alpha. Alpha plus alpha, 2 alpha. 2 alpha. So this comes out to be 2 theta. So phi is equal to 2 theta. So we have proved that. This is the question. Find minimum height of the plane mirror in which the boy can see his full image. H is the height of the boy. So if H is height of the boy and this green one is the plane mirror, so from the tip of his head light will enter his eyes, and from the feet also here light will enter his eyes. Simply, just if you make a bigger diagram, it will be more clear. Eyes, so make him wear a cap. Let's say simple like this. This light ray and this light, and from his feet these are the light. If you make this construction, minimum height of the mirror is this one, just the required height of the mirror, so that he can see his full image. Now there, if you extend it slightly, you see there are similar triangles and congruent triangles. Congruent triangles. Say this triangle and this triangle are congruent, and then this triangle and this triangle are congruent. So there, so this side, this, so this side is a x, and so this side is also x, and if this is y, this is also y, because of the congruent triangles. So this is actually y plus x, as you can see, and this is the total height, the height of the person, height of the person h is 2 into y plus x, right? So here h is 2 into y plus x, and minimum size of mirror, minimum size of mirror is equal to y plus x. So obviously it is equal to h by 2. So half the height is needed, minimum height is equal to h by 2, so that we can view his full image.